welcome everybody again to a new session of the diffusion chronometry lectures that we've been doing. And we're very pleased to have two very good speakers here today. But before I get to the introductions, I'd just like to tell you about the format of these talks that we've been running. Many of you have been here before, so it'll be familiar to you, but what we usually do is we have one talk at the beginning for about 30 minutes, then a few questions on that talk, and then we stop the questioning and go on to the second talk. And then after the second talk, we take questions on the second talk as well, but then we discuss both the talks together and questions that have come up on each one of those. Now, as it turns out, today we have two speakers who are going to touch on very similar subjects, the large silicic eruptions. So that's a very nice thing to have anyway for a discussion afterwards. So without much more on the introduction, let me just get to the speakers. So Steve Sparks and Jordan Lubbers are the two speakers today. The first speaker would be Steve Sparks, talking on large silicic magma bodies and very large magnitude explosive eruptions. And then Jordan will talk about thermal history of the Toba magmatic system, evidence from strontium diffusion in plagioclase, and hornblende, which is a new one. So we look forward to hearing about that one. Now, to introduce the speakers, one can use a cliche to say that to the volcanological community, Steve Sparks is a name that does need no introduction, but it'll be very difficult to list up everything that Steve has done, from which all of us have learned a lot. But I'll just go through a few things that I picked out that I thought might be worth useful to summing up Steve's career. So he's a geologist and a volcanologist, but I think he's by equal measure, he's a fluid dynamics person. And he's also done an incredible amount in terms of volcanic hazard assessment, setting up things to monitoring and so forth. And the interesting thing I found looking on the web was that he's gone on to apply some of those tools to modeling hazards from COVID and how it affects primary schools and things. So that's a measure of truly interdisciplinary work out there. So he spent most of his career in Bristol, where I gather, you may correct me if I'm wrong, he was involved in setting up the department, which is a very well-known department by now. He's been a trustee of the Natural History Museum in London. He has made very well-known and well-seen movies on volcanic hazards and risks and monitoring, and the Soufriere Hill Volcanic Observatory, which has produced a lot of very valuable information on volcanic eruptions, was also set up by him, and I guess he was one of the early directors on that. And for all of that, he has got, of course, a lot of awards. But I just mentioned that he was knighted in 2018, and he got the Betlesson Prize, which is one of the things that's considered to be kind of like the Nobel Prize by some, in 2015. So I think that kind of tells you what a distinguished speaker we have here today, and we're very pleased, Steve, to have you here. So I'll just let you take over from here and share your screen and give your talk. See if you can.
I think you have to shut.
I have to shut mine, so I've done that. Yeah. So you should be able to share your screen now.
Can you see that?
That's very good.
Okay. Well, thanks a lot for inviting me virtually to Bochum. What I'm going to discuss today is one of the big questions, I think, of the last 20 years or so is what are the processes which lead to the very large bodies of silicic magma that then can produce very large magnitude explosive eruptions. So we're talking about eruptions at the like Pinatubo, perhaps one in 100 years, with 5 cubic kilometers of magma. Silicic magma erupted. Tambora 1815, which is probably the sort of one in almost 1,000-year eruption on Earth, which produced 45. And then, of course, the big one, which Jordan will be talking about later, the Toba eruption, which produced the gigantic caldera in 74,000 years ago. So that's the question is, what are the processes which lead to these huge eruptions and the formation of these enormous calderas? I'm not entirely sure of the sort of the background and knowledge of the audience, so perhaps just to define one or two things. We're talking about the size of volcanic eruptions. We're talking about a magnitude, which is the log of the mass erupted -7, which gives us a scale which is by serendipity is almost the same as earthquakes. So the very biggest eruptions like Toba super eruptions are 9. And in fact, the so-called super eruptions are magnitude 8 or greater, or 400 cubic kilometers. And it's these really big eruptions that I'm going to sort of focus somewhat on today. Again, you can see here, just to give you the scale, this is Pinatubo. So I mentioned 5 cubic kilometers from space, producing a gigantic cloud. And one can just use one's imagination to think about what the eruptions like Toba and Asso and Crater Lake must have looked like. And if you'd looked at them from a satellite, probably a cloud thousands rather than hundreds of kilometers across. And again, just really, this is really background. We know that these eruptions are enormously, not only very big, but they're also devastatingly violent. And a good example of that is the 15 cubic kilometer eruption of Taupo in New Zealand in 180 AD. And you can see there on the map on the left-hand side, Lake Taupo and the deposit, which Colin Wilson has documented so beautifully, where we essentially erupted 15 cubic kilometers in about 15 minutes, according to Colin's estimates. So that's 220 million cubic meters per second. And I've superimposed it on London to just give you a sort of scale that the pyroclastic flow from this very violent event would have almost reached Cambridge and Oxford if the event had been in London. So it's really just to give you a scale. Another one that I've been working on more recently is the Asso eruption. So not only do these huge eruptions, this is one of the 4 super volcanic eruptions of the last 100,000 years, Asso 4, 87,000 years ago, and it erupted a few hundred cubic kilometers. And it spread pyroclastic flows to distances of up to 166 kilometers from the Asso caldera source. So very energetic flows like Taupo, just on a much bigger scale. And of course, it covered Japan and a lot of the eastern the Pacific sea floor to the east, with thick volcanic ash layers going thousands of kilometers. So that gives you a sense of the phenomena we're dealing with. And in order to get this, we have to find some sort of way of generating huge amounts of silicic magma, but accumulating it, as we'll see later, at a shallow level, and then erupting it. And so that's a rather mysterious process, because likely the typical rate at which silicic magma is generated time average over long periods of geological time is only a few cubic kilometers, perhaps per 1,000 years. So we've got to have something really rather special happening or interesting happening to accumulate. Now, of course, I think everybody is now familiar with this transcrustal magma system idea, that the crust is a sort of processing zone of basalt, which comes in at the bottom, fractionates, generates more evolved magmas, which then move up to higher levels and differentiate further, and perhaps melt the crust as well. And eventually, the product of that infiltration of the crust, certainly in arc systems and also hotspot systems like Yellowstone, for example, is the accumulation of large volumes of silicic melt at shallow level. And so that's the interesting question, is how does that happen? These zones, transcrustal magma systems, of course, are now increasingly observed through beautiful geophysical imaging. And you can see two examples here of a relatively small system of Merapi, where you can see the seismic anomalies and earthquake anomalies down to the Moho associated with that system. And then on the right-hand side is Uturuncu, which has been documented in some great detail. This is a slide from Simon Pritchard and sort of Matt Pritchard and colleagues, again showing the Uturuncu silicic system is underlain by a very large, huge geophysical anomaly. So we began to be able to image those. Again, another outcome of research in the last 10 or 20 years is evidence of crystal cardigos which come up with these magmas from a very wide range of depths. I'll talk a little bit about that later. There's evidence of cryptic fractionation amphibole at higher pressure. You don't necessarily see the either minerals that cause the fractionation, they can be left behind. And then you've got other evidence like sections through igneous crust like the Evroa zone and Sierra Fertigla Guaita, where you've got a piece of igneous crust on its side, and so you can sort of more or less walk up through the crust, seeing this sort of progressive development of a transcrustal magmatic system. So now going on to the sort of the timescales for generating, I'm going to start with a relatively small eruption by certainly by Toba standards, but nonetheless one of the biggest in the last 10,000 years on the Earth is the Santorini eruption of 1640 BC, where 80 cubic kilometers of homogeneous rhyolite was erupted and formed a caldera. The geological evidence that the volcano had been either dormant or at least very quiet for the preceding 18,000 years before the eruption. And we can start to see in the stratigraphy of a volcano like Santorini sort of cycles of activity which precede these really big eruptions. And so this is a section through the caldera of Santorini in the picture on the right, and you can see basalts and basalt, thick piles of basalt and basaltic andesite and andesite lava from 67,000 to 54,000 years, and then probably accumulating at about a cubic kilometer per 1,000 years. And then the volcano starts to become quieter, and we get a big silicic ignimbrite and a caldera at about 21,000 years. So much less activity between 54 and 21. And we've accumulated 30 cubic kilometers of magma. So there's a caldera formation. And then it goes after 21,000 years again into a relatively dormant or low activity. And we accumulate another 80 cubic kilometers for the Bronze Age eruption. So we start to see in the stratigraphy these sort of cyclic patterns of activity of mafic magma coming in and erupting, and then presumably not being able to get through the crust as easily and starting to stagnate, and leading to the generation of these large amounts of silicic magma. Now, I think the interest, one of the, again, an outcome of a lot of research by many people is, I think, a very interesting observation that the timescales for generating these silicic magma bodies is clearly very long, and there's stratigraphic evidence like that I've already shown you. but yet there seems to be in many systems evidence that these magma bodies accumulate in the upper crust in a much shorter periods, in the order of decades and millennia. And there's a couple of examples here. On the left, you can see something work by Tim Druitt and his colleagues at Clermont-Ferrand, looking at trace element zoning or minor element zoning in plagioclase. I guess Jordan will be talking about this later, but zoning patterns which require of overgrowths of crystals on older crystals, which seem to require really rather the patterns you see wouldn't be there if the crystals had been in this had happened over many tens of thousands of years. So we see evidence of much more rapid accumulation of magmas in the upper crust. So there's a bit of a dichotomy or a conundrum here, that we seem to have some evidence suggesting that differentiated melts form in the lower and middle crust in crystalline regimes over very long periods of time. And I've also shown you some of Carrie Cooper's some review paper on zircon ages in silicic magmas from all around the world. And I think the big message here again is that you get in many of these systems, you get older zircons which have been hanging around for tens or hundreds of thousands of years, which are erupted and commingled with the magma. So we get this conundrum of very different timescales, very long periods of time to generate the magmas in some way, but really rather short periods of accumulation in the very shallow crust before these big caldera forming eruptions. And of course, as a consequence of that, we get a lot of evidence of disequilibrium, magma mixing, and also in a number of cases, evidence for merging of separate magma bodies during this assembly process. Now, the one I'd like to talk about most, and it sort of, I guess, links in with the theme of your seminar series, the diffusion, is some work that Marit van der Lang did on some ignimbrites in northern Chile. This is called the Oxaya Formation. It's a Miocene formation, and it's essentially made of 4 gigantic ignimbrites, quite crystal-rich ignimbrites. So you can see the stratigraphy there. There's 4 of them: Pocan, Chile, Cardones, Molinos, and Oxaya. And her thesis was to do zircon dating and petrology and really document these ignimbrites. And these ignimbrites are a sort of a Toba scale eruption. The Cardones is at least 1,000 cubic kilometers in volume. And we see the sort of same evidence in these in this sequence. We see that, for example, we get zoned xanadine crystals with complex zoning. We get amphiboles, which seem to have compositions suggesting that they've come from much deeper than the final assembly point of the magma. So from the petrology, you can find that the emplacement of these magmas look like to be in the 6 to 9 kilometers depth, but it also shows that we're bringing up material which was much deeper in the crust, probably greater than 15 kilometers. And we see, as I'll show you in a moment, magma reservoirs were assembled in millions of years, yet again, like the previous example, it seems that the shallow magma chamber was assembled in decades or centuries, or certainly pretty rapidly. So that's the background of the study that the Cardones did. And this is the sort of key diagram from the paper we published in Nature that I want you to look at. And I'll spend a little bit of time explaining this. Here's our 4 ignimbrites, giant ignimbrites, the age on the vertical axis. And we've got three kinds of data here. We've got ages in red. There are Tim's dates of well-shaped zircons. So Marit spent a lot of time handpicking well-shaped euhedral zircons and trying to eliminate inherited zircons or older, more complex zircons from her data. And she analyzed those, and they have been used to interpret the eruption age. Now, if you look at the red, you can see that we've got roughly an eruption every million years. So we have the POC in Chile 22.7, then Cardones 22.9, Molenis 20.8, and the Oxaya 19.5. So what this data is showing is that this is a highly episodic process. We're getting one of these big eruptions roughly every million years. On the right hand, going to the yellow, the zircons that she sort of discarded, she then analyzed by uranium lead in the BGS labs using laser ablation, and you can see the data here, and these indeed are much older, and you can see that for any one ignimbrite, the data of these older inherited zircons, again rather like Carrie Cooper's data, is going back something like a million years. And then probably the most interesting data, which I still think has some puzzling elements, is in blue, light blue. These are sanidine crystals, which and each blue dot is a piece of a large sanidine. These ignimbrites have quite chunky sanidines of up to a centimeter in diameter, and so she extracted the sanidines from pumices, not from the ground mass, but from pumices to try and get their signature, and then used argonaude and laser to fusion of individual fragments to get a date. And what you see there is that there's clearly quite a lot of the sanidine which are near, in each case, which are close to the eruption age. There's a spectrum, but then there's a minority, but a significant minority, perhaps 10, 20% or more, which are giving you much, much older ages. And this is really interesting because you can see that the age spectrum is not identical to the old zircons, but it's broadly pretty similar. So we're seeing the same kind of evidence for older entrained crystals in the sanidines as we are in the zircons. Now, there's been a lot of talk about cold storage and the idea that these zircons are sort of dragged up from the source region during the generation assembly. But this is putting a little bit of a pressure on the cold storage idea, because this is sort of has to be ultra cold, because the sanidines, it's hard to. Marissa Tremblay has been working with, it's one of our co-authors from Purdue, and she's done some diffusion dating, which I'm going to, diffusion modeling, which I'm going to show you in a minute. But I'll give you the main message before showing you the Marissa's calculations. The main message is that if these old sanidines were much more than about 400, 450 degrees centigrade, it's hard to see how their old age would be retained. So these data are suggesting that some of the sanidines that have been incorporated are both old and they're very cold, and certainly subsolidus. And probably the best way of getting that sort of stuff is to reassimilate older plutons of similar character into the magma body. The other interesting thing is that Also, if these crystals are immersed in hot magma, the diffusion model, we know the temperatures are around 750 degrees centigrade. So if these crystals were immersed in hot magma for any length of time, they would should lose their age. And this is really the message from Marissa's modeling. On the left-hand side, she's looking at temperatures as a function of grain diameter to look at the, if you've got a particular age, let's say 25 million years, how big would that crystal have to be still, and how hot would it have to be in order to survive and keep the old age? And what you can see is the spectrum of ages are suggesting that the old sanidines have to be in the sort of 450, 350 degrees centigrade range, really quite cold. And then on the right-hand side, it's the same sort of calculation for different magma temperatures, but if you've got a sort of 1 centimeter wide sanidine grain, then and you want to still retain a 24 million year age in something which erupted 22 million years ago, then or sort of much sooner, then you're looking at only periods of decades, years to decades, for these crystals to be present. So our basic model is that these magmas, silicic magmas, are coming in to there's a shallow plutonic complex developing by invasion of these magmas. And when we get these big magma chambers, which are going to form the calderas, they're coming into earlier plutons of the same and disrupting them. Now, one thing I didn't mention, which I should have, and I just go back to here, is that you can see that some of the ages go back to 3 or 4 million years older than the oldest ignimbrite. And so this seems to be a case where there's a period of pluton emplacement with little or no volcanism that we know of taking place. And this suggests that the crust is sort of warming up towards creating these large magma bodies by silicic magma invading the upper crust and forming a plutonic complex which gets bigger and warmer with time, and eventually conditions are achieved to form a big eruption, a big magma chamber. And this is a very conceptual model, but this sort of shows you what our thinking is, that we have in the lower and middle crust, we have invasion of basalt. These basalts crystallize and differentiate and form silicic magma, which then very slowly squeezes out and forms layers of silicic magma in the crust. This is a very simplified, obviously, conceptual idea. And then that silicic magma from the middle crust, lower crust, pushes through and starts intruding the upper crust. But of course, the very earliest granites come into the cold upper crust and freeze, so we get no magma bodies. Later on, as this system evolves, the mafic mushy zone, hot zone, in the middle and lower crust starts to evolve and gets bigger and bigger and hotter and starts generating more and more silicic magma, and then repeatedly invades the upper crust. And then some point is reached when things in the upper crust are hot enough that we can start actually not assembling significant bodies of eruptible magma. And that's the general idea. Now, I'm not sure how I'm doing for time. I don't know if anybody could just check if I'm doing all right. I've got about 3 or 4 more slides. Is that all right? Hello?
Yes.
Sorry, that's okay. You can take your time.
Okay. Anyway, so this is a sort of general idea. Firstly, how do we generate the melt in the first place? The idea is that we have mafic intermediate magmas accumulating in the deep part of the crust, crystallizing, and then porous media effects squeezing out that melt to form layers at the top of the sort of mushy zone of silicic melt. And you can see this is a model from Matt Jackson's paper with John Blundy and I about that idea. And so I'm going to present to you a conceptual model of generating these layers of silicic magmas slowly in the middle crust, squeezing out silicic melts, and then looking at the instabilities that develop as a consequence of this generation of silicic melt layers in the sort of mushy hot zone. Just have a look at some of the details of Matt Jackson's numerical models. And what we're doing here is we're basically looking at the temperature at the top of a mushy zone formed by repeated emplacement of basalt. And you can see that on the right-hand side of the graph with time, you can see that the beginning, the first basalts, it's quite cool, so they freeze. And then as more and more of them come in repetitively, the crust heats up, middle crust heats up, the temperature goes up, and at then some point, the melt starts to be present. It becomes hot enough that the mush contains some melt, and that melt starts squeezing out. And in this particular model, it does so at 1.3 million years. You can see in the profiles, there's a profile at 0.97 million years, and then at 1.39 million years in the model. 0.97 is chosen because that's the point where the hot zone of accumulated basalt gets to the point where melt is permanently present. And that's once the melt's permanently present, it can start to migrate out and accumulate at the top. And so by the time we get to 1.39 years on the right hand of the four columns, you can see the profile of melt fraction. So in the model, there's a lid of silicic melt accumulating at the top once we've passed this threshold. And it's this accumulated layer that we're interested in. And so what we have is a sort of hybrid of melt ascent by Rayleigh-Taylor instability and then brittle failure and dike formation. And that depends a little bit on the strength of the crust. If it's a rather hot ductile crust, then the Rayleigh-Taylor part of the instability develops. If it's a strong crust, then that doesn't develop much, but the layer grows and fattens with time, and eventually, in both cases, reaches conditions for dike propagation and the rise of that silicic melt to the surface. Just looking at the Rayleigh-Taylor instability side, won't bother about the maths at this stage, but I'll just show you the experiment. This is a classic experiment done by Geological, where you've got a low viscosity brownie fluid, which is heavy, on top of a lighter fluid, much more viscous fluid. And we are interested in where there's a very large contrast between the viscosity of one layer and the other, which is what happens when you've got a silicic melt layer being generated underneath a viscous crust, an enormous viscosity contrast. And the interesting thing we learned from these experiments was basically that in the Earth, it's almost always true that the length scale over which the instability develops is the width of the system rather than the fastest growing wavelength, because the width of the system is always much smaller than the fastest growing wavelength. So it's the width which determines how fast this instability grows, you can see. Some very lovely experimental fluid mechanics by Jack Whitehead from Woods Hole generates these various theoretical models of how the instability grows and what its wavelength will be. Now, there's quite a lot here in this slide, but I'll just take you through it a little bit. We've got our silicic melt layer, which is growing with time, and the crust has, let's say, got a viscosity of 10 to the 18 Pascal seconds, and the wet rhyolite might have 10 to the 5 Pascal seconds, and a sort of a rate of growth might be a geologically reasonable range would be a few millimeters per year. And so we've got a range of H values, and we can put those in, and we can find that the fastest growing wavelength is either 138 or 308 kilometers. So that's pretty wide compared to the width of the plutons and calderas. So we know we should be in a sort of confined regime where the rate of growth is related to simply the width of the system. And I'll take to what I think is a very nice result from Gilles's work. And if you look at the little equation, that's one I just want to focus in, tau RTI, is simply the viscosity of the crust divided by the density difference between the melt and the crust and the width. And that turns out that that's a very simple and robust result, which comes about from this experimental work. So very simple in the end. So what we can do is we can put in various numbers we might like for the width of the system, 10, 20, 40 kilometers, a sort of scale of plutons and calderas. We can put in the viscosity of the crust. So we can have a rather weak crust, 10 to the 17, and a rather strong crust, 10 to the 19, perhaps a colder, stronger crust. And you can see that on the top row in the tables, when we plug things into the equations, we find that if the crust is rather weak, we get timescales for the instability of 10,000 years or so. If it's sort of 10 to the 18 Pascal seconds, we get tens of thousands of years, and if it's 10 to the 19, we get many hundreds of thousands of years. And then we can translate that into how much magma we've accumulated. And we can see that we can accumulate, particularly with a stronger crust, sort of volumes which are comparable to the volumes we want. So the point here is that the time scale of accumulation and instability is of the order of tens or hundreds of thousands of years, or even sort of could approach a million years. So we've got a mechanism of developing an instability, which takes a very long time. So it takes a long time to squeeze the melt out and make it unstable. And then we can do another calculation, which is that this flows up. It could be a dike or some sort of conduit to the shallow crust, and the crust collapses and the magma comes up, and we can match those two flow rates, the collapse of the crust with the ascent of the magma, and we find that that's a very fast process. So if we look at the diagram, just focus on the diagram for the moment, and then we can look at the equations, and you can see the flow rate is related to the conduit radius and divided by the viscosity, and we can put in typical numbers. And of course, the other we've got the viscosity contrast between the crust and the silicic magma layer. And again, the details don't matter, but you can see that if we put into the crustal radius of 5, 10, 20 kilometers, and we get a conduit radius out, we can calculate a flux, and we can find out how long it takes to accumulate the upper magma body once this exchange flow goes. Once the instability is taken off and the magma goes from the middle crust to the upper crust, then we're talking about tens to hundreds to perhaps a few thousand years. So we seem to have a mechanism here for explaining the very rapid transfer from this slowly accumulated melt through an exchange flow. So that's my conclusions. Silicic melts are generated, segregated, and stored in the middle crust. The storage times are of the order of 10 to the 4 to 10 to the 6, very slow processes of melt segregation and accumulation. Buoyancy eventually leads to failure of the accumulated silicic melt layers as they thicken and the buoyancy force goes up. The failure is governed by the crustal viscosity and strength, and the melts are transferred into the upper crust to form ephemeral magma chambers. And in that process, again, the crustal viscosity comes in, and these simple fluid pneumatic calculations suggest transfer of the order of decades, centuries, governed by crustal rheology. So it seems to be an explanation for these rapid assembly, evidence for rapid assembly. So I'll finish there. Thank you.
Thank you, Steve. That was very enlightening and very provides a lot of food for a lot of people. There's a lot of material for research for all kinds of directions here. So what we will do is we'll take maybe a couple of questions. You can type things into the chat or raise your hands and ask questions. And then we'll go to Jordan's talk and come back and then discuss the whole thing together, because it'll be nice, because with Jordan's talk, we'll see if you want a case study of the kind of thing that Steve's been talking about, and then we can deal with all of that together. But maybe a couple of questions quickly, whoever wants to speak up here. Eric.
Thanks for your talk, Steve. Can you hear me? Did I turn
I can, Eric, yes.
Okay, good. I was very interested in the old cold feldspars that were dated. I'm puzzled why they would still be sanidine. If they had been old and cold for a very long time, they should have converted to some more ordered state and might look more xenolithic. Did you see, is there any evidence of that? And
we didn't see that, but I think that's partly because we didn't look for it. And there's a question, of course, when they're heated up, whether to what extent they might be annealed. But unfortunately, the order in which the research occurred, those argon fusion dates were obtained very late, in fact, after her PhD, and that's about the last thing she was able to do. So it would be very interesting to go and look at the order, do a proper mineral physics study of those crystals. So I suppose they could be crypto perthites or something like that, but we didn't have any evidence. I mean, we only looked at them under SEM and probe, where those would be not resolvable. But it's certainly a very good point that that's what you might expect. So it is a bit of a puzzle. I mean, if somebody can think of another way of making them old somehow, then that would be great. But yes, it's a bit.
And while one is at it, that'd be interesting to look at the ordering state of the feldspar as well.
Yes. Yes.
That will depend on the time it has sat at high temperatures.
Yes. Yeah. Yeah. So I don't have a really very good answer to that, except that, as I say, we didn't. It's I think it'd be an interesting thing for somebody to do.
thanks.
I think other people have started to see the old sanidines as well. I think Wes Hildreth and colleagues had some in the Bishop Tuff, and there's some in the Toba, I think, that Darren Mark has found.
Okay.
So is there one more question, perhaps, before we move on, or shall we just continue on? Well, I had a few questions, but maybe we just go on with the second talk, give people time to digest what they heard, and then we can go on to discussing both of them together. So again, thanks, Steve, and let me just introduce Jordan quickly. So Jordan did a BS in geology at University of Wisconsin at Oshkosh, MS at Michigan Tech University, and then he went on to do PhD in Oregon State. And I understand the work he'll be reporting on today is largely from his PhD, if not all of it. And finishing his PhD, he's done, which he did with Adam Kent and working with Sean De Silva. And since then, he's moved on to the USGS as a mendenhall postdoc and is currently located in Alaska. So thank you again, Jordan, for getting up at an early hour and be willing to give us the talk. So I'll let you share your screen and see what you have to say.
All right. All right. How does that look?
Looks good. Yeah, no, it's good.
All right. Thanks for the introduction. Yeah, I'm Jordan, and I'm a postdoc at the Alaska Volcano Observatory up in Anchorage, mostly doing tephra stuff now. But we're going to talk a little bit about my PhD work, or one of the chapters from my PhD, where we use plagioclase and hornblende diffusion, or strontium diffusion and plagioclase and hornblende, to kind of constrain the amount of time that the magma system that produced the youngest Toba tuff existed at or above eruptible temperatures. So a little bit of a background on caldera-forming magmatic systems. Steve already gave a nice introduction on this, but taking a top-down approach, this figure from Wilson and others from a review paper a couple years ago shows really nicely that they exist across all tectonic settings. They produce the largest explosive eruptions on Earth, and also help kind of modulate the evolution and composition of the continental crust. They cover their tracks really well because they result in these big cataclysmic explosive events. And how I kind of like to think of them is these really long-lived, complex multi-phase fluid systems, which are kind of, because we can't directly observe them, are very tough to kind of unravel the magmatic processes, or the processes that form these eruptions. So what we're going to focus on for this talk is one small part of the puzzle, I guess, with the plumbing systems of these magmatic systems, and that's how long do caldera-forming magmatic systems exist at conditions required to produce large volumes of eruptible magma. So of their overall, if you want to anthropomorphize them, lifetime, how long do they exist at temperatures capable of producing large volumes of eruptible melt or magma? Switching to a side view, we have this nice figure from Cashman and others that nobody's ever seen before. That just does a really nice job of explaining how you have this incremental emplacement of magmas over a long period of time, and this results in this pretty complex crustal ladder that's both stratified in temperature and composition. And you can imagine somewhere in there, there's a large silicic magma reservoir. And then expanding on this, Wilson and others from that same review paper, switching to a side view, showed really nicely that because there's all sorts of unique things going on spatially with a given large caldera-forming magmatic system, tectonic setting, local country rock, magma emplacement rates, things like that, there's really no one-size-fits-all set of rules that can basically be applied to these systems. And so they all have their own unique thermal and chemical characteristics, which is something that, makes them a little bit harder to interpret, but also that's part of the fun. Defining what I guess me and my co-authors mean by a thermal history. So we're going to define a thermal history basically as a magma reservoir's long-term thermal state, time, temperature, path, if you want to think of it that way, using this figure on the bottom from a review paper by Miller in 2016, which is basically adapted from Adam and Carey's paper, or Carey and Adam's paper from 2014, where you have this time, temperature, path, and on the, I guess, absolute end members of this, you have a solidus temperature and a liquidus temperature, but there's a temperature somewhere in between there, whereby the magma exists in what we call an eruptible state. So below this eruptible state and above the solidus, you have a mixture of melt and crystals that is too crystalline or too viscous to be mobile to get out of the ground. And between this temperature and the liquidus, you have some fraction of eruptible magma. And that's kind of shown here in this cartoon in panel B in the upper right, where you might have this network of sills that are interconnected or maybe not connected. And this is where maybe defining a system as a whole gets a little bit tricky, especially if these are long-lived and producing eruptions over a long period of time, say like the Toba tuff, like we're going to look at, or the Toba magmatic system. And the thing that I want you to take away from here is that many petrologic tools are really good for interpreting magma reservoir processes, but they only offer snapshots into what's going on in the magma reservoir at one specific moment in time. So if we want to look at this time temperature path, we need another tool that's going to do that. And because we're in a diffusion chronometry seminar series, I'm not going to go over this in too much detail, but diffusion offers a really good way to kind of quantify this. So from a review paper by Phil Costa and others a few years ago, they have this nice schematic that, on the bottom there, you have a crystal that's growing in a magma at time 0 or time 1. It grows some composition crystal, and then the melt chemistry changes, which then grows a new composition rim or zone around the crystal. And if that crystal then sits at magmatic temperatures for long enough, that zone boundary relaxes due to diffusion, and we can quantify that. And the nice thing about this is that the rate at which this happens is a function of temperature. So if a mineral is sitting at high temperatures for long enough durations, it gets recorded via diffusive equilibration. So if we didn't see that, if basically the slope of that diffusion curve can give us some idea of how long we're sitting at high temperatures. So with these large caldera magmatic systems and quantifying the amount of time that they exist at temperatures that are capable of producing large volumes of eruptible melt, what temperatures are we necessarily concerned with? And from this, we take some of Richard Bradshaw's dissertation work, which is now in review at JPET, where he did a bunch of melts modeling for large caldera-forming magmatic systems and looking at the crystallinity and viscosity of the remaining melt there. And what he found was that around 750 plus or minus 10 degrees, with a lot of these caldera-forming magmatic systems, they reach crystal fraction of around 40 to 60% crystals, and also melt viscosities such that they become ineruptible. This overall crystal fraction that they become eruptible or uneruptible is a very complex multi-phase fluid problem. But what we see at around 750 degrees on the left here, in these red and blue lines, at very small changes in temperature, we get large changes in both viscosity and crystallinity. So we can use 750 plus or minus 10 to really approximate this eruptible, not eruptible threshold for a lot of large caldera-forming magmatic systems. And that's what we're going to do with Toba here as well, even though it's not on this list. Moving on to the youngest Toba tuff, a little bit of background here. So the youngest Toba tuff is the youngest caldera-forming magmatic system from Toba caldera. There's the middle Toba tuff and the oldest Toba tuff at 400,000 and or 500,000 and 850,000 years ago, roughly. And this one produced a lot of eruptive material, more than 2,500 cubic kilometers. And basically what we're going to focus on here is the two different pumice types that we find in the youngest Toba tuff. And they look something like this. The light brown pumice on the top there is what we're going to call banded pumice. You can see nice big quartz grains in there. And then this lighter colored pumice on the bottom is what we're just going to call normal pumice. And these pumice display a large range in composition, and they also have a very diverse mineral assemblage. There's quartz, 2 feldspars, also some minor orthopyroxene, there's amphibole, even a little bit of phaelite, and minor phases like zircon and alunite and other good things in there. And with the amphibole present, we can do some thermometry and do a little bit of diffusion chronometry with a not so new, but kind of new chronometer. So Mary Reed and Jorge Vasquez have done a lot of work on the zircons and alanites over the years. And this is just a nice figure from their 2017 paper where they show that there's quite a protracted storage time for these zircons and alanites in this magma reservoir, which points to this being a long-lived magmatic system, kind of what Steve was talking about a little bit earlier. But what we're concerned with here is, of this long lifetime, how long is it existing at a state that's capable of producing eruptible volumes of magma? And so if we switch to a little bit of a geochemical perspective, Nick Pierce and others, and Casey Tierney and Mary Reed have been looking at a lot of the glass chemistry from the youngest Toba tuff. Pierce and others are looking at distal ash in marine sediment, coarse proximal tephra and pumice and things like that. And Casey and Mary have been looking at melt inclusions. And what they found is that there's really shown nicely in this figure on the right is that there's 5 discrete pumice populations geochemically. And you can plot up whatever discriminators you want. This is yttrium versus barium. Strontium and barium show the same thing, incompatible trace element ratios, so show very similar things. And it's not a continuous array of populations. These are all kind of their own sub-parallel groups, which is quite fascinating. And what Pierce and others in 2019 proposed, based on similar melt extraction pressures from the rhyolite melt skew barometer, is that this leads to something that they've interpreted as 5 laterally discrete magma reservoirs that then erupted all at one time. And on the left figure, they also go on to say that these populations kind of inherit chemical signatures from previous Toba caldera eruptions, so the OTT and the middle Toba tuff. So the workflow from this project, there's no field work. We already had samples in hand from Otto Muchek. And so we take her samples, which are, I guess, shown here in the stars. So we have 2 north of the caldera and 1 to the east of the caldera, and crush them up, find some happy plage, hit them with some analytical work, so the microprobe and laser ablation ICP-MS, and then we do a bunch of diffusion modeling and maybe a little bit of petrologic modeling, and we try to make some interpretations from that. Our analytical data, so all the stuff that's grayed out is what's been collected, but for this talk, we're going to focus on our high resolution trace element transects from laser ablation ICP-MS. So these transects are basically continuous lines that are built on 5 micron by 50 micron rectangular spots that then are stepped 5 microns. So it gets us a really nice high resolution, but not convoluted line across a compositional boundary. And we have that for plage and amphibole here. Looking at some of the BSEs from these plagioclase, you know, they're pretty classic looking silicic plage or plage from large caldera forming magmatic systems. Rarely do we find a whole grain. They have a mixture of happy and unhappy textures, oscillatory zoning, but also some cores that are resorbed, quite high anorthite, maybe suggesting that they've been inherited from an older eruption. And we're not going to delve into the textures too much here. Just want to highlight that all the red lines are transects that we have laser ablation transects for. All the red lines are laser ablation transects, and so something that we've tried to model diffusive equilibration across. Shifting over to the chemistry of the youngest Toba tuff plage, just plotted here are barium versus anorthite on the left and strontium versus anorthite on the right. Strontium versus anorthite in plage land is a pretty common first pass, I guess, for is diffusion chronometry even possible with these plage, or are they all in equilibrium? Because strontium is compatible in plage as we fractionate a magma and anorthite of the plage goes down, we're progressively pulling out strontium, and so what we should see is this positive correlation here, which is the opposite of what I guess partitioning alone would predict, which is kind of shown by these black lines here for all the different melt compositions from glass analyses that we have. And this is a good sign, I guess, because this means that diffusion modeling for strontium is something that we could do, something that we can explore. We must be somewhere between our initial state and a full diffusive equilibration, which would have a similar negative correlation to anorthite, or negative correlation with anorthite, like these black lines here. This isn't really something, a rule of thumb that we can use for other trace elements in plage that are largely incompatible, barium and magnesium, which makes discerning between growth and diffusion a little bit harder. So we're just going to stick with strontium for now. This looks very similar, regardless of which partitioning model you use, whether it's the Doman and Blundy model, which is thermodynamic and lattice strain based, or an equilibrium, or not equilibrium, an empirical Arrhenius based model like Bindeman and others, or Roger Nielsen's model from 2017. Switching over to the amphibole. These are pretty large. They're huge. The scale bars are kind of hard to see on here, but these are on the orders of a few millimeters. So picking these out and mounting them really wasn't that challenging of a task. If you squint your eyes and look really hard at the computer screen, you can see some BSE zoning. And this is even with the brightness and contrast jacked way up, which is why all the oxides in there look very, very white. But they have a whole suite of inclusions in them. They have pyroxene, plage, oxides, so we can get some nice formation temperatures using the plage amphibole thermometer, or we do amphibole only thermometry. But the really nice thing about these amphiboles is that they've been looked at before by Gardner and others in 2002, and what they found is that based on some experimental work, and never getting amphibole to crystallize over a wide range of pressures and temperatures, that they assumed that the youngest Toba tuff magmatic system was formed at, these had to be xenocrysts in the magmatic system. And they also did some radiometric dating and found that they could be as potentially old as 1.5 million years. Similarly to what Steve was talking about with the I believe diffusive argon loss with the sanidines. In the previous talk, they also did some modeling like this in that paper and showed that if they wanted to retain these old ages, they couldn't have existed in the youngest Toba magmatic system for more than, depending on the crystal, tens to a couple thousand years. So these are incorporated into the magma system, system-wide, relatively late in the formation of this magma reservoir. Looking at some of the formation temperatures of these amphibole, these are just using some amphibole-only thermometers from Keith Patirka's 2016 papers, one that's pressure dependent, one that's pressure independent. It doesn't really matter here. You can see that they give basically the same answer, roughly 800 degrees plus or minus 30 to 40. So relatively cool formation temperatures for the amphibole. And then shifting over to some of the amphibole chemistry, looking at incompatible trace element ratios and europium anomalies, we see that there's kind of two groups here on the left in panel A there that's split roughly around strontium yttrium ratio of 0.7 there. So the stuff that's in the red in the bottom left is a little bit separate from the stuff that's in the orange to blue in the upper right there. And that holds true for our trace element spots in the dark symbols and our trace element transects in the kind of transparent symbols there. And these high europium anomaly, high strontium yttrium, high barium niobium amphiboles are also our hottest and highest magnesium number amphiboles as well. If we shift to a transect view of these amphiboles, we see that these incompatible trace element signatures are all consistent across the transects as well, which might help provide some context for what these rim zones on these amphiboles actually mean. Getting kind of thrown into a new crystallization environment there. You can see that we're shifting from barium niobium ratios of 9 all the way down to like 2 strontium yttrium ratios of over 1. So in this one group, in the upper right here on panel A, down to the bottom left in panel A there. Our glass chemistry that we measured on the laser shows exactly what Nick Pierce and Casey Tierney and Mary Reed have been showing. And even though we only have 3 samples here, we're really sampling kind of the whole suite of compositional variability within the youngest Toba tuff, which is pretty remarkable to me. Even within the same samples, we're having multiple pumice types here. So this teal symbol. Getting into our plage diffusion modeling setup. So Fidel Cosa and others in 2003 came up with this really nice but somewhat complicated solution to the diffusion equation for plage, which kind of necessitates a little bit extra care when we're setting up the diffusion model as far as equilibrium profiles and our initial profile from which diffusion is starting here. And this is largely the result of the magnesium flux, or in this case, strontium flux in plage being the result of 2 components. One from it diffusing in response to its own concentration gradient, and the other is the fact that its chemical potential is related strongly to the anorthite composition of that plage. And so what we do is, with number 1 here, is we start with our observed data. We have our strontium profile on Earth black lines, and we have our anorthite profile in those blue lines there. And then we can take both of those things and calculate a partition coefficient for each point in that profile. And using just basic partitioning relationships, we calculate a profile that would be in equilibrium with the most rimward value, or the most rimward analysis there, which is similar to what the melt composition actually is, plus or minus a few ppm. So we get our solid equilibrium profile. So this is basically what that diffusion equation is striving for, or the final endpoint, I guess, if you want to think of it that way. And then what we can also do is calculate a melt composition that should be in equilibrium with that solid black line there. And that's what's shown on the right. So we take that melt profile that should be in equilibrium with that solid measured profile, and we create a simple melt evolution scenario that assumes any deviation from that is due to diffusion. So this just says that, on the left side of this step function, we have a melt at composition 1, say around like 65 parts per million strontium. Then all of a sudden the melt goes up to 110 parts per million strontium, and then back down to around 65 parts per million strontium. And we can do this for any partitioning model scenario, and kind of results, which is what's shown here between the various partitioning models. Then after this, what we do is we back calculate a solid profile from that simplified melt profile, right? Just the partition coefficient at each given point times the concentration of the simple melt profile. And this gives us this dashed gray line, and that's what our assumed initial profile is prior to any diffusion happening there. Next, we're going to forward model isothermal diffusion at discrete time steps until T is really, really large. And then we're just going to go into those discrete time steps, quantify a misfit between that and the observed data, and get our best fit, our best fit discrete time scale, which is shown kind of on the bottom here. And then we can also plot up some reference curves, which are these thin red, purple, and brown lines here. And our green is our best fit diffusion model there. And you can see that they all look somewhat similar, although on the right here, the Doman and Blundy partitioning model seems to be able to capture the observed data a little bit better in this scenario. So this is kind of a nice, I guess, bake-off, if you will, between various partitioning models and how well they can describe the the observed data. What we're also going to do here is we're going to do a simple Monte Carlo situation to assess the uncertainties of these diffusion models, so we can vary the composition of each point based on its analytical uncertainty and run 1,000 diffusion models, and then fit those each one of those 1,000 models with a best fit time to come up with a distribution, something like this middle panel here for each diffusion model. And this kind of gives us, based on our analytical uncertainty, what the range of possible timescales would be for this. And so what we see with our plage here is that we kind of run a whole gambit of timescales from quite short, about 25 years for that that plage in the top right there, all the way down to our longest measured strontium diffusion timescale at about 1,500 years in this plage on the right. And you can see that these are kind of different spots on these plages where this long timescale looks like it's coming from a more interior zone. It's tough to say whether or not this is actually a core or not, because we didn't really, I guess, have this mounted along specific crystallographic axes or anything like that. And crystal edges are a little bit tough to find in some of these plage, but it's more interior. So it makes sense that this might have a longer residence time at or above 750 degrees. Shifting over to our amphibole diffusion setup. This is a little simpler than plage, which is a welcome relief. So in 1995, Brabander and Giletti published a paper on strontium diffusion kinetics and amphiboles and their significance to thermal history determinations, which I stumbled across in some lit review some point in grad school. And then seeing these large amphiboles in the youngest Toba tuff was like, well, okay, strontium diffusion in hornblende is kind of in a nice little sweet spot. It's not super slow, it's not super fast, so we should be able to get some useful information here. And it's got, according to this paper, no compositional or orientation controls that we know of, so it should be a relatively simple solution to fix second law with a constant d value here. And so what we did is we measured these high resolution transects across these zones in amphibole. And here our initial profiles are just simple step functions at the midpoints of gradients, kind of similar to how you would approach a titanium and quartz situation or like a barium or strontium insanity sort of situation. And what we see here is a couple things. Using this sort of methodology, we can produce really nice fits to the diffusion equation, and also that these timescales are ordered by, or longer by about an order of magnitude. The shortest one that was calculated is about 280 years in this top profile here, but the longest one is all the way down to about 5,600 years. So these are significantly longer than our plage timescales, which if we take the interpretation of these being xenocrysts in the magmatic system, checks out. They've had a longer magmatic resident or longer time at high T, just because they're not just phenocrysts, they've also been in a magma before this and sitting in the crust potentially. Looking at all of our diffusion models, so we were able to get good fits to our trace element profiles in most of our plage. Not all of these produce good fits to the diffusion equation, so we kind of just toss those out. So we have 35 out of 45 plage that are kind of, if we look at these blue spots here, are in the decades to centuries at or above 750 degrees here. And then we have 12 out of our 22 amphiboles that had concentration gradients that were able to be modeled. And those are an order of magnitude longer in the centuries to millennia at or above 750 degrees. And if we incorporate, the sample location or pumice type into this, we see that that doesn't really matter. They're all exhibiting the same or similar thermal histories. So there's no statistical difference that you can tease out of sampling location. That might be due to low N, but also that they're just experiencing similar thermal histories. There was one grain that we found, and this was the first, I guess, plage that, or silicic plage, that I've ever seen that closely matched its calculated equilibrium profile, which was pretty cool. I guess from a plage diffusion standpoint, I remember plotting this out and being like, whoa, okay, that's new. It matches this black observed line in the bottom left, matches the shape and magnitude relatively well of our calculated equilibrium profile. And it also has a negative slope with anorthite, which from talking about before, remember, means that it is either matching its partitioning controlled situation, or it's experienced significant diffusive equilibration. And this kind of makes, I guess, sense regardless of which partitioning model you want to use. Broadly, that absolute magnitude of that trough in the observed profile isn't really that important. Really, what is the kind of dead giveaway that we might be in some sort of equilibrium state is that in the top center panel here, we have our strontium profile in black and our anorthite profile in blue. We see that they're relatively inverted from one another. So putting this together, we have numerous discrete glass populations from the youngest Toba tuff that are exhibiting a wide compositional range here. But these populations have similar thermal histories, or similar, thermal states that are relatively indistinguishable from one another. And these thermal histories suggest that these amphibole and plagioclase grains are experiencing relatively short times over 750 degrees compared to zircon residence times, or compared to the overall, lifetime of this magmatic reservoir, which is shown by these zircon and alunite crystallization ages on the right here. Some future work, because this is very much a work in progress. Now we're kind of in the stage of comparing the influence of partitioning model and calculated diffusion time. So this is kind of a model output summary that we get for each grain that we model here, where you have the anorthite profile in the upper left. You have some various partitioning curves in the middle panel there, and the BSE image with the transect in the upper right. And then we have our fits to our model fits for each given partitioning model. We also add in the much magnesium model if we're going to do magnesium diffusion. And then we have our best, or our Monte Carlo distribution of our best fit times, or that give us some sort of like 2 sigma uncertainty on these timescales, factoring in analytical uncertainty there. The other thing we want to do is compare magnesium and strontium diffusion times. One thing that I found doing magnesium and strontium diffusion in the Cerro-Galán ignimbrite was that there's kind of a big disconnect between these calculated diffusion timescales at or above 750 degrees. And this is something that, I think we could maybe reconcile with different partitioning models. And so this is kind of the plan here, is to incorporate some new magnesium partitioning stuff and try to figure out kind of if we can reconcile those differences. Then the final thing we want to do is apply better context for these diffusion times. So this is just a figure from a paper that came out last year on the Cerro-Galán ignimbrite, where we did a similar methodology with plage diffusion, but a way to kind of address some context here, right? Because one solution to these all being short timescales at or above 750 degrees is that they're all just young ephemeral plage at the end of the magma reservoir's evolution right before eruption. So that, of course, they're going to be short timescales. They're young themselves. And so what we did is we tried to use barium concentrations in the melt that's in equilibrium with the plage to kind of address whether or not these plagioclase are existing in a melt that has experienced late stage crystallization of biotite and sanidine. And because those phases exist in the Toba magmatic system, we think we can apply a similar methodology to this study as well. With that, I want to say thank you to Otto for providing samples of the diffusion community at large. I think when I was really first getting into this, I attended the Hawaii Goldschmidt diffusion workshop, and that really, I think, knocked a couple of years off my PhD by saving me a lot of banging my head against the wall, figuring out the math and things like that. And in general, everyone's been super supportive, helping me figure out or try to figure out these really complicated phenomenon. And then the open source community for helping develop the tools requisite for modeling diffusion. If you want to know basically how I did everything, you can scan that QR code, and there's a GitHub repository on the other end there that shows all the Python code that was used to do this. So thank you.
Thank you so much, Jordan. That was a nice step-by-step run through to the way you get to these results and some of the stumbling blocks that you have along the way. And so now we are ready for questions on both the talks. So please, whoever has whatever they want to find out of. So Steve, yes.
Yeah, Jordan, a lovely talk, fantastic data there. Thanks very much. I wondered how if I've got it right, you assume a temperature of 750. How sensitive are your results to that assumption? Because we're now seeing evidence of mobility in magmas which have quite a lot higher crystal content than the traditional sort of threshold of maybe 50% crystals. Particularly if you've got different grain sizes, you can get higher crystal indices and the magma can be still quite mobile. So I wonder whether that 750, if you took it down to 700, would the results be all that different or not?
Yeah, so we kind of tested this out here. I'll reshare my screen. You see that figure there?
Mm-hmm. Yes.
Yeah, so basically ran the same diffusion model at different temperatures, and you can see that if we go down to about 700, it's maybe 10 times longer in diffusion time. So you can just basically take all those time scales and just make them 10 times longer. So I guess you would be in the centuries to millennia area now.
Yeah, so could you sort of bring the amphibole and the plagioclase frequency curves together?
Well, I guess if I shifted the plagioclase temperatures, I'd have to shift the amphibole temperatures as well. So those would, I guess, shift similarly. Although, I guess, the amphibole is an interesting story with them potentially being xenocrysts and things like that. So I think there's definitely more work to be done on them. The amphibole transects that we gathered, we didn't really know if we would see anything on the other side. So we didn't devote a ton of analytical time to them. Turns out there's a lot of good data there. So it'd be nice to go back and mount up some more and really kind of figure out what's going on. But yeah.
Yeah.
Thanks, Jordan. Other questions? If there aren't, I'll ask you one, John. So on your plagioclase crystals, the rim composition of the strontiums, are they the same on all the crystals or are they different?
They're not all the same. They're slightly different. They're different enough. So I don't have an exact number there, but I remember plotting this up, and it's not like we can just use the concentration of I guess one concentration that they're striving to be in equilibrium with. Also, I think this is convoluted by the observation that there's all these different pumice populations as well. So we might be sampling numerous, I guess, if you want to use the Pierce interpretation, different little magma pockets, their populations there. So they're not all the same, no.
So, because that's one thing I've been thinking about, that strontium being compatible, and if you're looking at small magma mushes, then depending on how the size of the mush, the strontium may get depleted to different extents, and that would lead to different boundary conditions on the different crystals. And I was just wondering if you have played with that as a parameter in your modeling to see what it does to timescales.
I've played around with using like an overall, I guess, average, and then using like the most rimward analysis, right? Because not all of these transects are also rim analyses either. There's like some smack dab in the mantle of the grain or at the core of the grain. So in that situation, I don't use the actual rim composition itself, but it doesn't really, I guess the overall variation in the strontium itself in the system isn't large enough that I've noticed a massive difference in the calculated timescales. I guess with the uncertainty of everything else, right? The D value, the temperature, and the analytical uncertainty, and the questions that we're trying to answer, I think, you know, it of course will change your answers, but maybe not outside of like the decades to centuries realm that we're
range that you have
with here. Yeah.
Okay. Mm-hmm. Philip, you have a question? Or
I do. Thanks, Jordan, for your talk. I was wondering, you showed in your amphibole data, you showed the strontium zonation, and then you kind of color coded it by these other parameters like barium, yttrium, and so on. How much are they truly correlated? Because if it's diffusion, wouldn't you think that they are somewhat decoupled? Or yeah, just commenting on how much you worry that this is actually just growth and signatures related to that.
Right. I guess that is definitely a possibility because there's no major element controls on strontium diffusion, or I guess not nice things that we can help constrain initial profiles with. I just assumed an initial step function across that concentration gradient. So you could think of those as, right, the quote maximum timescales, that cop-out answer. But it is, of course, possible that could be much more relaxed from an initial profile and be even shorter. Maybe bring it down somewhere in the decades to centuries if we make it more similar to the actual observed curve there. So I haven't quite figured out a way how to really constrain good boundary conditions on those amphibole models yet. This is kind of a first pass, just using a simple step function there. Yeah, that's a great observation.
No, it makes sense, and it's just like I was just curious how well these these different kind of features are correlated, these different chemical signatures, right? European anomaly and all this stuff that you're mentioning, because their diffusivities are likely different.
Right. Yeah, it would be something that would be really nice to explore in the future. Do kind of a deep dive into this.
See that Jamshid has a question. I'm sorry. Okay, I'll come to you.
Great.
Jamshid, go ahead.
Thanks. Thank you, Shumit. Hi, Jordan. Jamshid here. Also
Jamshid,
in Alaska.
Good morning.
Good morning. Great talk. Thanks. I was wondering about your crystals, your phenocrysts that have multiple distinct zones, like a core, mantle, and rim. And across those profiles, it looks like you had like multiple distinct like initial profiles. So I was wondering if from these types of profiles, if you're trying to model two separate like magmatic processes that are forming like a first normally zoned and reversely zoned profile. And so are you extracting multiple timescales from those profiles, assuming that the innermost zone is still diffusing before the outermost boundary is even formed yet? And how do you account for like temperature? Do you see the temperature is the same throughout all that growth and diffusion process? Curious for my own application, so I appreciate your input.
Yeah, so with those plaids that have multiple transects in them, basically what I'm doing is I'm just getting a best fit time at or above 750 for each one. And fortunately, what we see is that in that situation where, you know, you might have a rim transect and then a middle transect and then a core transect, the core one's always longer than the rim, or the core one's always longer than the middle, and the middle one's always longer than the rim, which is nice, and kind of giving us answers that we would expect there. I haven't done anything to try to get at, using that for any sort of crystal growth rates or anything beyond that, just because, with these diffusion times, the uncertainties are large enough where it might start to get a little arm wavy. But I guess those are things that you could start to try to look at and starting to back out specific processes there. Yeah.
Cool. Great. Thanks.
Thank you. Ralph, you had a question.
Yeah, hello, Jordan. Thank you for the talk. So I think I didn't really fully understand how you were able to reconstruct the initial strontium profile. Can you explain that quickly again, please?
Yeah. Just reshare really quick. Go up to that slide. Shot it. Okay. So this is basically, I guess we'll start here. So if we have our black observed data, so that's what we measured with the laser, and then we get a partition coefficient using whichever model we want there. And then we use that to construct a melt profile that, should be in equilibrium with that composition. So just solving for CL in that bottom equation there. And what we do then is we just assume in the next slide here, a very simplified version of that, like a simple two-stage melt evolution model where you're going from one composition up to another one and then back down. And then we're back calculating a solid profile from that simplified profile there, which is why it kind of has that bunny-eared shape because of the anorthite not being that exact shape as well. But I guess if you made this initial profile flat, that would inherently assume that there's a lot more complexity going on in the melt evolution at that time to make it flat, other than a simple two-stage melt evolution model. So that this was kind of, I guess, a simpler magma reservoir evolution approach than that. And I guess early on I kind of compared. Initially I had been doing it the other way, and I couldn't get a lot of good fits to the observed data. And then turns out making some initial profiles like this ended up solving that problem pretty well, and allowing us to really match the observed data via diffusion a lot better. Of course, when the anorthite profile, I guess, from Fidel's 2003 paper, right? That thing on the bottom there, when the anorthite profile is also flat, like this, then they're both then the initial profile is also flat like this, and you can get nice solutions that way. But in these silicic plage, it's really kind of a mess as far as what the anorthite profile is doing.
I tried this for other systems many times, and it's really maybe a smart way of doing that. But there is one assumption is then that the melt composition for the major elements doesn't change then during this evolution. Huh? You'd only consider then, because that would also affect the partition coefficients.
Yeah, so I guess we calculate the partition coefficient at each step as a function of what's going on here and this anorthite profile. So it is kind of incorporating that, but it's a simplified version of that. Of course, we could make something that's more complicated than this plug shape. Just programmatically, that's a little bit of a pain to do. So it's just easier. I've toyed around with doing some interpolation, making slanted initial profiles and stuff like that, which you can do. But ultimately, it doesn't get you that different of an answer, I guess. And this seemed to work pretty okay. Yeah,
I think because in this case, a lot of the memory from the initial profile was lost. I guess some final result is not so sensitive to the detailed initial profile. That's what I think.
Mm-hmm. Yeah, and I toyed around with, you can adjust the width and the height of this, right? Like one obvious thing, be like, oh, well, know that it's not a much taller, I guess, plug? And you can't really produce good fits via diffusion that way. So that was kind of a first order check on, okay, this is probably broadly the height and width of that initial boundary condition as well. And petrologically, it's not unreasonable either, I guess.
Okay, thank you.
So there are other questions. Not, I was going to ask Steve something. So Steve, in that model that you have a deeper magma chamber that's differentiating for a long time to generate this silica-rich melt, and then at some point it starts migrating upwards to form the shallow magma chamber, and then it erupts. So I was just wondering, so the chamber below is differentiating for a much longer time scale. That means there has to be a heat source that's that long. So is that?
No, that's not right, because in the sense that the heat source, the temperature goes up in the source in the source zone, and then you reach a temperature where melt is present. And then the temperature doesn't have to go up. The melt just has to separate out into a layer. So the temperature doesn't really have to change very much.
But it has to stay at that level for.
It has to. Yes, that's right. It has to. If you have to have a sort of, I guess, an advection of heat from basalt below in order to keep the pot boiling, as it were.
Right. So for that length of time, so you have to have
that length of time, yeah. So I think that's the. So you don't really have to heat everything. You have to heat the general body up by simply you're bringing in more heat than you dissipate out, and so the temperature goes up and eventually reaches the point where silicic melt is present, and then that can slowly segregate and form layers of magma.
Right. So you have to sustain that for quite some time, and then once it starts moving up, if it comes up and has this geological stability and erupts, then it erupts. But wouldn't there be possibilities where it would start segregating from the lower magma chamber but doesn't erupt? What would it do then? Make a shallow pluton?
Form granite plutons, I imagine.
So is that, you think, how? Because I've heard people say that the shallow plutons are not the equivalents of unerupted magma chamber. So I'd like to hear your thoughts on that.
I don't know. I've not seen any sort of strong evidence that they're not related. I mean, in the case of the Andean rocks that we looked at, the ages, both of the older zircons and the sanidines, go back 3 or 4 million years earlier than the first known volcanic rocks. And there's some sediments underneath those ignimbrites which have detrital zircons, and they don't have any zircons in that age range.
I see.
So it looks like there's a period of, or it's consistent, let's say, with a period of pluton growth which might have lasted 2 or 3, 4 million years without necessarily very much erupting at all.
Okay, and then once in a while it's big enough to cause an eruption.
And then the idea is, of course, you need that sort of incubation of heat. You keep needing to put more and more silicic magma in the upper crust in order to warm it up to the point at which it can sort of host a big magma body.
Mm-hmm.
So that I think that's the sort of general notion. I mean, I thought Jordan's it was a question I had for Jordan. 2 questions that are sort of linked in a way. Jordan, I thought the amphibole data. I mean, I wondered what your interpretation of it is. You think that they are anticrysts and they could go back 1.5 million. Some of them could go back as 1.5 million years. So those amphiboles that you're studying, couldn't they be anticrysts from shallow plutons that have disintegrated into the magma body?
Yeah, I guess that's the interpretation that the Gardner 2002 paper kind of implied, in a similar situation to the sanidines that you were looking at. They couldn't have retained their age and been in the Toba magmatic system for more than decades to a few thousand years. Otherwise, they would have been reset. So they had to be, I guess their interpretation was, one, anti-crust, but two, stored fairly cool and then reincorporated into the magmatic system.
Yeah. And I think that's one of the interesting things, that both parallel observations that you're getting, you appear to be getting plutonic anticrysts being incorporated into these magma bodies a relatively short time before the eruption. I mean, the accumulation may take rather longer, but it looks like a sort of instability developing in the magma body itself, and you can sort of imagine bits of pluton being digested by the accumulating magma body.
Yeah, and I think it's kind of hard to in like systems like Toba or Golan, when they erupt very similar compositions repeatedly over the span of a few million years, right? Like those Sarah Golan eruptions or the Toba Tuff eruptions, they're all very similar compositions. So presumably it's just like scavenging itself, which makes discerning these things chemically in the trace element chemistry kind of really hard to tease out, and quite an interesting puzzle to really try to get after.
Well, multiple minerals and multiple elements is the way to it. And I have a question on that, but I see questions. Gerhard, Philip, and Ralph. So Gerhard, perhaps first. Got
yeah,
are you there?
Yeah, okay, thank you.
Yeah.
A comment and a question to Steve. I mean, the comment would be that the interesting part of what you said about the priming of the system is that there is not a sign of any volcanism prior to the ignimbrites. It's not just that there is no zircons, there is also no immediate mafic andesite or anything. On the other hand, right after all those ignimbrites, you have these what I call the shield andesites. They look to be high temperature, hardly any phenocrest, rather dry andesites that make these shields that sit directly on top of those ignimbrites. So I think this is your priming magma, but why doesn't it erupt before? You don't see a trace of the mafic and the heat input into the system before the ignimbrites actually do their big bang. So what's your thought on that?
Well, yes, I mean, I sort of agree with what you say, Gerhard, that's a very interesting, but I think the point is, of course, the zircons in this pre-ignimbrite range are in the ignimbrites themselves. So they give evidence of zircon and sanidine crystallization before 2 or 3 million years, perhaps even 4 million years before anything much emerges on the surface. So there's magmatism going on. There's silicic magma appears to be being generated. It's just not erupting. So I think that sort of goes towards the view that you can get plutonism without much volcanism. Now, what the tectonic reason for that is I guess another matter. But I mean, I'm very struck that those Azapa sediments, which the detrital zircons, don't have anything in that age range. They're all sort of 30 million years plus.
Exactly. That's my point, that there isn't any precursor magmatism to the system.
Well, there's no precursor volcanism.
No no precursor volcanism. I mean, usually when you see these large systems, there's scattered volcanism all around, and then the system seems to gear up to become ignimbritic and silicic. And then it is maintained by continued recharge at temperatures, as you said, that are high enough to keep the system alive. But why doesn't it come out before at the surface? That's my problem, and I thought you had an idea, maybe.
Well, I mean, I suppose the way of doing that is to have a relatively slow rate of magma. If you like, magma fluxing, because if you have a low rate of magma fluxing, it takes an awful lot longer to, if you think of sort of Katrina and N models and other people's models of
Mhm.
sort of making a pluton hot enough to contain eruptible magma, then if you drop to a low flux rate, then you're not evicting enough. You're basically heating things up very slowly, so it takes a long time. The incubation period is a very long time. So if you're down to 1 or 2 millimeters per year, sort of a 1 millimeter per year rate, then you may simply not get large magma bodies formed.
Okay, thanks.
Well, I have Philip and Ralph here, but I'd just like to throw in 2 things quickly. First, I got a thing on chat from Blake that he and Calvin Miller have a paper that's related to what we're talking about. And he was saying it's a shameless plug, and I asked him to put it on the chat for everybody here, because that's why we're here, to share what all is going on. And because I have, and I'll get to you, Philip and Ralph, in a minute, but because of what I've got and Steve here, I was just wondering, because I was just with the students at the Siebengebirge the last weekend, and there you have basalts before, basalts afterwards, and in between you have a big tuff. So would that fit into this idea of that you are putting in a lot of basalts, and then in between at some point you have just enough material to trigger the whole silicic thing? I'd like to hear your thoughts on that.
Well, that was my basic thinking, that there should be something like that. And my feeling is a little bit different from what Steve just said. Maybe you create a silicic melt layer so fast that you can no longer traverse it with the basalts, because one issue is that there is not a lot of magmatism in the 30 to 40 million years old, and then there is a 10 to 12 million year old gap with no magmatism. And one idea was that you had a flat slab situation, and then the slab catastrophically falls off, and then you bring in all the asthenosphere. You put in a lot of basalts into the base of the crust, but the crust is also thick and hot that it never comes to the surface, and creates a silicic magma layer at depth so fast that you never see the basaltic andesites at the surface. So that is my from the top of my head, my forced interpretation based on the observation that we have, but it's not really constrained in any way by thermal or any other constraints.
That's great.
Just to sort of I haven't got it in front of me, so I can't sort of check, but I think it's right that the plate reconstructions of that time suggests that the rate of subduction increased rather dramatically in that sort of 30 million to 25 million, 23 million year period. So it sort of started off, if you equate plate subduction rate with basalt generation rate or magma generation rate, it suggests it sort of almost that what you say and what I've been saying are actually not mutually exclusive. They it looks like the plate was subducting slow, and then it accelerated, and the big ignimbrites seemed to come out at the point where it became a sort of super. I think the spreading rates are around 15 centimeters per year or more at about that time.
And also catastrophic steepening after a flat
slab. Yes, yeah. So in a way, both could be true, couldn't they?
Been nice to try all of these things together. So, Philip, you've been waiting for a long time, yeah.
Well, I mean, just a quick comment: the flat slab subduction story that then switches over into dramatic ignimbrites. I mean, that's something that's very common in the Great Basin with all the ignimbrite flare up there. So that would make perfect sense. But quick, maybe to Steve, whether you can comment on the argon-argon ages. I was wondering, are these well-defined plateaus in the paper themselves? There's no figures or mentioning of how good these argon-argon ages actually are.
I thought there was some supplementary material with the. I think they. I mean, you probably have to ask my co-author Darren Mark about that, but I remember them being pretty decent flat flat ones. So I can't remember the big anything odd about them.
Yeah, I'm just wondering because I couldn't find anything in the supplement. That's why I'm wondering.
No,
Thanks.
No, that's a good. It's a good. Yeah, I can follow that up. Follow that up.
Thanks.
Ralph.
Yeah, just a quick question for John related to the amphibole diffusion data. How does the composition of your amphibole compares to the composition of the amphibole from the diffusion data? Because we know amphibole can vary quite a bit in composition, and that can have dramatic effects also on the diffusion rates.
Off the top of my head, I don't really know how, I guess, how similar they are. But my understanding from that paper was that they kind of explored some of that in hornblende, and it was within the uncertainties of the Arrhenius parameters for the D value. So it wasn't super large, so certainly nothing like compositional controls in Plag. I'll have to go through and read that again, but it would be nice to play around with that because these amphiboles are so big that, you know, we can mount them and get crystallographic control relatively easily. And then just kind of play around with, like, say, a max and min, you know, on compositional space, maybe if it's like factor of 2, 5 order of magnitude, not, but that's one thing I hadn't explored. To be completely honest, I didn't think that this amphibole stuff would really amount to much. And then all of a sudden we saw some profiles and we plotted them up. So it's like, okay, let's hit the ground running and kind of proof of concept this. But I think that there's a lot of ground to be made there and explore. And it'd be great to see. I just remember reading at the end of the paper that there's a sentence about, you know, these findings have implications for looking at thermal histories or like thermal states of magma systems. And then I'm looking through the literature and trying to find amphibole diffusion papers, and I didn't find a single one. So hoping more people maybe slap some high resolution transects across their amphiboles, see what they can find, because I think there's a lot of good information there.
You're pouring
for us.
honey into my ears because I was writing a proposal to measure diffusion coefficients in amphibole, and I need some reasons. You're supplying me.
There we go. Happy to be that reason.
I might just add one point going back to the argon. We had some discussion when we were writing up that paper with Marissa and Darren Mark about, and one of the things I'd wondered was what happens to all the argon when it goes out of the crystals. Where does it go to? It's probably got not, if it's a huge magma body, it's probably, or magma reservoir system or Pluton, it probably doesn't go very far. Or so can that sort of build? I just wondered whether there was any evidence of sort of argon actually, old argon building up somehow in the interstices and the grain boundaries, and therefore perhaps the argon diffusion's more complicated than we think. And I asked Marissa, maybe somebody who's listening could answer this question, whether anybody had studied that, and she only could find one. She thought there was only one paper which had looked at this at very high, at quite different conditions.
I think that's an old issue that people keep thinking about, but nobody seems to find an answer.
No, that's right. So I think, I mean, just going back to one of the main points, of course, is that the old zircons, which I think everyone would probably be okay with, have got the sort of basically the same age spectrum as the old alkali feldspars, the old sanidines.
Mm-hmm.
So that gives a sort of level of confidence. I mean, if it was something random, you might not expect them to give broadly the same picture.
Yeah, I mean, there've been talk about whether argon gets trapped in domain boundaries within crystals or not, yes, whether it diffuses out freely or not. And it'd be very useful to try to map the argon distribution in the crystals, but it's just an old thing.
And nobody seems to have done any work on it.
Yeah.
Yeah.
Well, people keep doing it, but it just it's one of those things where the more people look at it, the more complicated it gets.
Yeah.
But
Can I say something?
Hi, Mike.
Hi. First of all, the amount of argon is really small. And secondly, the argon is in the atmosphere today. I mean, the argon 40-36 ratio is dominated by all the argon produced by potassium decay. So it's whatever, if there's a fluid phase in the magma, it's going to end up in the atmosphere. It's not
Right,
the amount in the magmas is incredibly small. If you do the count for the number of atoms that are involved, it's almost nothing, I would say.
Right. Is it nothing when it's just the grain, if it's completely solid, if it's in completely solid rock and it's just along the grain boundaries?
You mean, would it be enough to make a separate fluid phase, for example? Or,
Yes,
but it just absorbed on the grain boundaries.
Yes, it concentrates on the grain boundaries.
Yeah. Well, it's not very compatible in the crystals, so it will try to get out of the crystals if it can.
So the thing there, Mike, is
that are kind of an open structure, so it probably could stay in them for some time as well.
Yeah, seeing has been that those diffusion rates are for diffusion in an ideal crystal. And if you have sort of twin plane boundaries or whatever, there's some suggestions that things can get trapped there and then they can just be sitting there for much longer time. And, you cannot, then your diffusion calculations are not giving you the real time scale, is the thinking.
Yes, because but I don't know if the ones that Steve talked about, if they measured using a laser to do the argon by laser heating of a single spot, then you could see the argon released and see if it's if the argon 40-36 ratio, whatever is as well as the argon 40-39, if it's magmatic like, or if it's been related to atmospheric contamination and giving older ages and real. But like Steve said, the correspondence between the zircon data and the overlap of these argon ages suggests they're pretty consistent between the two.
Yeah. I mean, if it was some random error, it's very unlikely it'll end up in exactly the same spot. Yeah, it's true. So yeah, I mean, as I thought, a lot of food for thought, a lot of ideas for new proposals is what.
One more question while
yeah, please.
For Jordan, I haven't done the calculations that you assumed equilibrium partitioning behavior to evaluate these diffusion flattened concentration profiles. Is it dependent on what if these discontinuities represent times of rapid crystal growth and the partitioning was not at equilibrium values? Would that change or influence your results? So
yeah, I guess if. Sorry, go ahead.
Sorry.
Oh, I didn't catch the last part there.
Oh, if you use the equilibrium partition coefficients in evaluating the diffusion profiles, what if they're not equilibrium values? For example, during fast crystal growth, we may not have equilibrium partitioning.
Yeah, then I guess that equilibrium profile would look something different. In that situation, I don't really necessarily know what you would do. Maybe Sumit or Ralph would care to chime in there, but yeah, Ralph can go ahead. But
I mean, the equilibrium profile that you calculate would not look different because that's based on equilibrium.
Yes.
The other problem is just to reconstruct the initial profile based on partition coefficients in equilibrium. Yeah, I mean, of course, what you can argue is that for fast growth, I think then the effective partition coefficient is usually closer to more closer to 1. Yeah, so because it's just taking up the element, as it is, the same kind of concentration as in the melt if it's very fast. but there are also maybe some other kinetic parameters playing a role. But since strontium is already relatively is compatible and the partition is close to 1, I don't think it would make a huge difference in your rough guess of the initial profile that you do anyway.
Yeah, I think I would expect it to be more important for crystals with partition coefficients far away from 1.
Yeah,
for the more highly incompatible elements, it would be more significant. I would guess or predict.
And in cases where the diffusion is not gone enough to lose memory of the initial state. Yeah. The one good thing in his samples is that it seems to have lost much of the memory of the initial state. So if you have uncertainties in that initial state, that doesn't affect the result as much. I mean, it does some, of course.
Yeah, so you still have sort of an infinite reservoir on both ends of the profiles, essentially.
That's the assumption, I guess.
Yeah.
Yeah, I mean, really, the initial profile is like the hardest. This is the pledge. That for me is the hardest, or where maybe the most uncertainty comes in, and all of the steps that I was talking about. That's where you're making all these assumptions and things. I mean, it seems to work okay. I guess Ralph, your model produces better, I guess, overall. Not enough slides to show them all here, but fits to the observed data with those calculated initial profiles. It also, because it predicts that strontium is less compatible at lower anorthites than like the Nielsen and Bindeman models do. Like those get super compatible at low anorthites, and these plages are AN 30 to 50 basically, so they're pretty albitic. And so the deviations, I guess, you get penalized more for incorrect assumptions using those like Bindeman and Nielsen models. More like if you look at, let's see here, like this figure here, the like bunny ears stuff. Here, you can see that they're more pronounced at the edges for like slightly missing the mark with the respective anorthite profile here, this blue line, because the partition coefficient is so much bigger with Ilya and Rogers' model. When you back calculate stuff and you have slight deviations from there, it gets it can get out of hand really fast, whereas we don't necessarily see that with the initial profiles calculated from the Doman and Blundy model, which then ends up making the fits to the observed data a lot better there. But the initial profile is like, bane of my existence, kind of a pain, but not impossible.
I mean, I think that you finally can reproduce your measured profile is some hint that your initial estimate is not that bad, because you cannot produce the same profile from any kind of arbitrary initial profile. I mean, the final profile you measure, as long as it's not in equilibrium, gives you some. You cannot back calculate diffusion, but at least constrain the initial profile based on that.
Right. And, with those reference curves for, say, 1,000, 10,000 years, whatever you want to put for your reference curve, there's always uncertainties with these things, but you're ballparking at least like what the general shape of the observed data is, right? If you get too long at high temperatures, now you start to mimic, an equilibrium profile shape, at least, right? Where you start getting inverted from the anorthite profile, and we just generally don't see that in the strontium, except for that one grain in the YTT plage, which is a very fascinating grain that kept me up at night. But
that's a general pattern that the profile shapes actually give some clue as to what the initial profile may have looked like, and if you're starting with something completely wrong, then don't get there. Now, as always, it's been fascinating to have all this discussion, and we say 2 hours and we're over that now, but it is always good to have the discussion and have this exchanges where we go off from the talk and actually discuss other things as well. So thank all of you for being here, and particularly Jordan for getting up early to do this, and Steve for taking the time for coming out and discussing all of this. This model that you showed would be a very valuable one going forward, trying to set up what we should be modeling with diffusion modeling. So that'll, I'm sure, give a lot of food for thought for a lot of people. So thank you, everybody, again, and we'll be back again in a month. Okay? So, bye-bye.